Because physics can be a very challenging course, because now you're applying these concepts and building the math around them, I want to go through a bit of what we did today, talking about distance and displacement, and then how we can use those to calculate speed, velocity, and acceleration, and how they're related, at least on a beginning level, to get you started on some of these. So let's take an example situation where a whale swims due east for 6.9 kilometers, then turns around and swims west for 1.8 kilometers. We're going to say that the trip takes it 45 minutes in total, so they're both directions, and I want to determine several things from that. So the first thing I'm going to do is draw this out, not the whale, just its motion. So he starts and he goes 6.9 kilometers. Well, that's not east. East. And then he turns around and swims 1.8 kilometers west. So my first question is, what's the distance that the whale swam? Well, distance is not a vector. Distance is a scalar, so it doesn't depend on direction. So for distance question, we would add the two. 6.9 kilometers plus 1.8 kilometers equals what? 8.7 kilometers swum. Now this is different than what displacement the whale experienced, because displacement is really only from the origin to the place where we stop looking. So that would actually be the difference, because the 1.8 kilometers was in the opposite direction. We have to treat these like vectors. So we'd have 6.9 kilometers minus 1.8 kilometers for a total of 5.1 kilometers. And because displacement is a vector, we have to specify that that was in the east direction. I should say too, the abbreviation for these is often like an X. I'm going to use X this time. Could be a D or an S, but it doesn't really matter at the end of the day. Displacement then is the same value, but it's got the vector symbol over it, because now direction matters. As we scroll down, I want to know a couple other things. The average speed while swimming. Now, average here means that we just look overall the total distance. So speed is distance over time. We look at the total distance swum divided by the total amount of time it took. This doesn't take into account the fact that sometimes a whale might have been swimming faster or slower. Doesn't matter. This is an average over that whole time. So he swam 8.7 kilometers. We saw up above that it took 45 minutes. So I just need to divide those two out. 8.7 divided by 45 gives me a total of 0.19333, but two sig figs. And then units, kilometers per minute. That doesn't change. I just rewrite them in a sideways form instead of vertically. Velocity is a little different now, because velocity is a vector, and it uses the displacement of our whale divided by the time. The displacement we figured out was 5.1 kilometers east. But the time is no different than before. That trip still took 45 minutes, even though we're sort of ignoring the section of where the whale went farther east and came back. This is only looking at the beginning and end points. So we're going to divide out the numbers. 5.1 divided by 45 gives me 0.113, two sig figs again, so 0.11. Use the units as before, kilometers per minute. And now we have to tack on the direction which we get from the displacement, east. We can also rearrange any of these if we are given a velocity or speed and we want to find the displacement. Well, we have to use algebra to rearrange that, but the important bits are here. The other question I'm going to talk about is a motorcycle. This motorcycle is accelerating from rest, you know it was coming, to 11 meters per second in 2.3 seconds. What is its acceleration? Well, acceleration is a vector. Acceleration, remember, is a measurement of the change in velocity over time. And recall that velocity is a vector itself, so it's got a magnitude, how fast is it going in this case, and a direction. So be thinking about how could something with a magnitude and direction change. Any change in velocity means that there is an acceleration. In this calculation, it's often useful to, instead of writing delta v for this, just write out that we have a final velocity minus initial. That's what delta means. Final value minus initial value, in this case with velocity, over the amount of time going. Well, the motorcycle accelerates from rest. That means we're starting at rest. That is an indicator of our initial velocity. Rest means it's not moving, so it's velocity of 0. And it's moving to, or it's accelerating to 11 meters per second. Because there is no direction on 0, we don't really have to worry about it in this case, but we will have a problem down below where we have to worry about it. I'm just going to put in my values now. I know it's go 11 meters per second is the final velocity minus 0 meters per second for my initial. Over the time it took, 2.3 seconds, acceleration then is 11 divided by 2.3. 4.78, so 4.8 units here. I have meters per second over seconds. Those seconds don't cancel. That's not the way math works. So meters per second is a really good way to do it. I like that because it reminds me that it's how much am I changing in velocity, meters per second, every second. But it's okay to write that in the shorthand way too, 4.8 meters per second squared. That's how you're going to see it in books. Going down to another example with this now, same motorcycle, it's cruising at 11 meters per second, and it applies the brakes. The rider applies the brakes and stops in 1.3 seconds. What is the acceleration now? Same question, or at least same setup. It'd be final velocity minus initial velocity. Both of those are vectors when it's important for us to do that. But now let's look at it. It is going 11 meters per second, and then it stops. So see, clearly stopping comes later, which would make it a final velocity of 0, because stopping is 0. The initial velocity up here is 11 meters per second, so let's put those in. I'd have 0 minus 11 meters per second. Over the time it took, 1.3 second time it takes. So I'd take that negative 11 divided by 1.3, and I'd find a negative 8.46, so negative 8.5 meters per second again. So this is indicating that the acceleration is actually in the opposite direction of the velocity. So think of this think of how these vectors add. Acceleration is the vector that causes velocity to change. So if we have our initial velocity up here of 0, and we're changing to our new velocity of 11 meters per second, acceleration is the thing that's got to get us there. So in order for it to go from 0 to there, we have to be pushing in that direction. Likewise, down here, we are going from a velocity of 11 meters per second to a velocity of 0. So the acceleration has to be pushing in the opposite direction to shorten that arrow, essentially, as a way of thinking of it. Third and final question on acceleration. If the motorcycle were instead to slow from 11 meters per second to 7 meters per second in 2.5 seconds, what would its acceleration be? So it said it's from 11 meters per second, so we know that it's starting there, that's our initial velocity, to 7 meters per second, that must be our final velocity because it's going to that, and we know the time. The final minus the initial over time So our V final is 7 meters per second minus our initial of 11 meters per second over 2.5 seconds. So our acceleration, 7 minus 11 is negative 4, divided by our time of 2.5 seconds. We get negative 1.6 units, again meters, per second. So in other words, we're going from our 11 meters per second to 7 meters per second. Well, that's going to make our acceleration arrow has to fill in that gap. It's got to be going the opposite direction. So it's actually to the left, even though all of our velocities are to the right. If we saw that it was picking up speed, we can kind of think of that graphically. So let's say that we're going from a slow speed to a faster speed. Well, then our acceleration has to be in that direction. Or if we throw something upwards, say, we'll say that the upwards velocity, our initial velocity, is going like that, but as we know, it stops, slows down, starts coming back down. When we catch it, it'll be in the opposite direction. Well, then our acceleration must be going from changing our initial into our final, like that. We'll deal more with changing direction, and you might have a problem or two about that. But just keep in mind that if we've got, say, an initial velocity in the positive direction, maybe it's 15 meters per second. If we change directions, our final velocity could be negative, maybe negative 10 meters per second. And our acceleration then, final minus initial, over time, we have to keep these positive and negative signs because these are all vectors, and that direction is really important. So we'd have a negative 10 meters per second minus a 15 meters per second. So that's negative 25 meters per second on the top, divided by, I'm just throwing it up there, whatever time we have. Keep track of which direction, and you should be okay.